That problem? Yes.
It has movement. Because that was probably the weirdest thing I've ever heard someone say in a class.
Yeah, it just,
Relative to that problem, there's not much second.
it was so weird and random.
It was.
He was so casual about it too.
I know.
Well, I mean, he's trying to be so cool, and it wasn't.
Yeah.
Oh, we're going?
We're getting that beginning too.
Okay, you gotta get the beginning.
Gotta get that. The introduction.
Great, it's like 54.
Moving on. Let's talk about that problem that I just gave back. It was the one with the fighter jet, and he's at the bottom, and you have to figure out the radius. Okay, here's the deal. When he's at the bottom, your total force, right, is going to be the force centrifugal plus Fg. So here's the question. When you're at the bottom of this loop, okay, whether it's a roller coaster or whatever, can you ever be in 0G, which is kind of poetic, I know. No, why? Why can't you be in 0G at the bottom? Yeah, as I'm sitting here, I'm pulling 1G, right? I am pulling 1G right now because of the fact that I'm at the bottom of, in effect, a loop, right? So the minimum I'm going to have Fg. Minimum, okay? Don't have that. So this is what you're going to experience, 9 Fg, okay? And what a lot of you did is you just said 9 Fg equal to that force centripetal. Gravity is providing you one of those, okay? So when you're at the top, you're at the bottom, start with this and then go from there, okay? You have to start with this idea that you're either subtracting or you're adding depending upon where you're at. Okay. Now, let's talk about the Kepler assignment. So, anybody have any specific questions? Cool.
Oh.
Oh, May.
Number 9.
Okay, number 9. So, here's the setup on number 9. Here's the Earth, here's the Moon, right? Now, you have to remember that you have to look at this from a historical perspective in terms of what Kepler knew. He was doing this late 1500s, early 1600s, okay? We did not know anything about Newton's laws of gravitational motion, could not calculate it, could not do anything. In Kepler's mind, all he was trying to find is a method to describe the motions of the planets. He thought, okay, there should be a simple mathematical formula to make this happen. He did not know the distances. He did not know the distance from the Earth to the Sun. He just said, hey, I'm all about ratios. Okay, I don't care about distances. We'll figure that out later. So he said, okay, like I'm going to let the distance from the Sun to the Earth be one astronomical unit. Boom. There. I have a nice number to work with. So we're going to apply that same mindset to the Earth and the Moon. Okay? Now, there's actually 2 different periods of the Moon. One is the actual time that it takes, and the other one is because the Earth is moving and the Moon is moving. So one's like 29, one's 27, depending upon which period of the Moon you're going to use. It's not the point of the question. So you're told that a satellite is 1/4 of the way to the Moon. So here's what you can do. I don't care what you do. But you've got 4 variables here. You've got the period of the satellite squared over the period of the Moon squared is going to equal the rate of the satellite cubed over the radius of the Moon. I don't care which one you put on top. Okay, I don't care. But you can't cross them over. If you're going to start with the satellite on top, you have to have the satellite on top over here. If you start with the Moon here, put the Moon over here. Doesn't matter, okay? Literally, don't care. They just have to be the same. Now, you have 4 variables, and if you're not sure what to do, write these out. Okay, I got the period of the satellite, I've got the period of the Moon, I've got the radius of the satellite, I've got the radius of the Moon. You don't know the actual distances. Those numbers aren't there. So, What do you want the period of the moon to be? 1. Okay? I'm going to make this one lunar unit of time. Okay? That's it. I don't know what it is. I don't care what it is. It's a ratio. So then I'm going to let the period of the satellite be my unknown. I don't know what that number is. Okay? I don't know, don't care. So at this point, you're told that the radius of the satellite is 1/4 that of the moon. It's 1/4, right?
Yeah.
Yeah. So here are your two options. I don't care. If you let the distance from the Earth to the moon be 1 unit of distance, okay, instead of an astronomical unit, we're going to let it be a moon unit, okay, a mu versus an AU, okay? So if you let this distance be 1, then the distance of the satellite is going to be 0.25, right, or 1/4. Now, the other thing that you could do is you could let the period to, let's say you really like the number 1, fantastic, and you hate fractions, I don't blame you. So one option is that you could let the distance from the Earth to the satellite have a value of 1. But then you let the distance to the moon have a value of 4. Okay? You'd still get the same answer. But here's the whole key to this. When you find the period of the satellite, does your period, just think through this. Does the period of the satellite have to be bigger or smaller than the period of the moon? Smaller, because it's inside that orbit. Okay? And later on you'll see that why that works with gravitational potential energy and kinetic energy. And that's something that, you know, Kepler didn't talk about, Kepler didn't know. We didn't know anything about conservation of angular momentum. We didn't know anything about, you know, gravity, anything like that. So Kepler was literally, he was like the news guy. He says, I don't know why it works, but it works. Here's the news. I'll let somebody else figure it out. My work is done, drops the microphone, walks off the stage. So, when you get this answer, and I tell you explicitly, I want this answer as the multiple of the moon's period. So let's say this works out to be 0.3. So you would say, here's how you would express your answer. Period of the satellite is 0.3 times that of the moon's. That's all you have to say. That's it. Boom. Now, the beauty of that is that once you actually figure out the period of the moon, then you can take that fraction, multiply it by the actual period of the moon. There's the actual period of the satellite. Okay? So Kepler was all about ratios. That was it. Anyway.
Ballpark on that one?
Very much less than 0.5.
Okay.
So
Might
like,
involve a 1.
so like period satellite is whatever times.
The period of the moon.
Okay.
That's it. That's all you have to say. That's it.
Right now.
Your answer to number 5 should be something around your first teenage birthday. And your answer to number 8 should be something-ish around the legal drinking age. It's an ish. Okay? Beauty of it is, if you're on this planet, you turn 1, you can drink. Because it takes so long to make one path around the sun. Can't wait for my first birthday. I will drink. Okay.
It's a joke.
It's a joke.
I didn't understand the joke. What's the joke?
If you consider a year to be one path around the sun, like we're here on Earth. So if you're on this planet on problem number 8, because it takes about 21 years to complete one orbit, you can drink when you turn 1 year.
You comedian, you.
No, it wasn't a comedian. It was a logic issue.
It was a joke.
A comedian would be so. This planet walks into the bar and says, "Hey, bartender," that would be a comedian, you know?
Well, when people laugh.
It was a sign.
I just flew in from, Pluto, boy, my arm's tired. No.
I think you're trying to be funny right now, and I think it's funny, but you're like doing it in like a sarcastic way. I like it.
Burkamp, you will not believe what happened during our
You have to let it tell you.
Oh, yes, this is a good song.
So we're in there slaving.
Snap my ruler. My third load.
Okay.
This is my fourth load.
But listen,
How?
listen, you
To
don't
be
know.
fair, this is all Grant's fault.
Yes, no.
Oh, hey, it's Grant's fault.
Yes,
Hold
okay,
on.
Grant.
I gave it to him so he could line up his paper or whatever.
Yeah.
And I never got it back.
Okay,
No,
well,
yes, you
okay,
did.
here's
That's
the
a
thing.
lie. That's
We're
a
always working on stuff, and he's like, oh, beg for it back. He made me do this. I had to get on my knees and beg for it, okay?
Yeah,
So
so-
finally, tables have turned. I'm like, all right, if you want your ruler back, beg for it. And he's like, shut up, blah, blah, blah.
Grant questioned.
He questioned, he was like,
Hunter's strength
honestly,
to
are
snap
you
it.
even strong enough to break that ruler? At that point, I had
The
to
game was on.
like, my intention was not.
He was questioning
Yes.
the validity of your man card.
Exactly. If I would have let him like walk all over me there, it would have been a long year. You know?
Yeah.
But
So what? Next thing you know, there's a piece
What
of
do you know?
plastic
Yeah,
flying.
what do you know?
You get
There's
LU.
How do you do the
everywhere.
Grant has one.
Entropy happens.
Third one I've witnessed.
Okay,
Yeah, Grant,
anyway,
how far?
anything else on what's going to
Is
try
it on the
so?
LU?
Huh?
Is it unit LU?
Yeah, all right, lunar unit.
So it's
Pass your car.
this.
Okay. Maddie, shut that down. I got stuff to do. Okay.
I got
that's all.
lucky
It's all
today.
turned
I
into
know, I saw.
I was late.
Okay. So what we're gonna do, we're gonna kind of work through this collectively, kind of in stages.
Yes.
Okay? So you need the graph from Friday, which has the polar coordinates plotted on it for the path of Mercury. Okay? Yeah, hopefully you haven't handed it in. Yes, okay, because you gotta have that to do what we're gonna do today. So basically what we're gonna do is we're gonna look at three things. We're gonna see if Mercury obeys Kepler's laws. Then we're going to see if we can validate that, if we think it does, and then we're going to use that as a transition into how Newton would explain Kepler's laws. Okay? So Kepler early 1600s, Newton late 1600s, we got to go through a transition phase. So first off, you've got all of this data from Mercury. Okay? Collected this over a period of time. Here's this complete orbital loop of Mercury. So we're going to go through this. It's going to be pretty simple at the beginning. It's going to get much more complex towards the end. So, question number one, looking at a graph, does the orbit of Mercury support Kepler's first law? Does it look like an ellipse? Yeah. Now, if everybody else had been right, if Mercury had moved in a circle, that process would have been much simpler. Okay, I probably wouldn't have even had you graph it, because all you'd have to do is just take like a compass, put it in the middle, and draw a perfect circle, and oh, boom, there we go, there's the path of Mercury. Okay, it's not, it's an ellipse. So there's question number one.
So yes, it's an ellipse.
Yes, that's all you have to say. That's it.
Can we get more questions like that?
No,
Like
that was your gift. Merry Christmas.
At
Yay.
least I got a 1 out of 80 on this.
That is true. If you miss number one, yeah,
We're done.
I put exactly yes, it is an ellipse.
That is what I put.
beautiful.
So,
You use and instead of
it is a ellipse.
And ellipse.
And.
a. And.
That's what I
E's
put
and
it.
vowel.
You just, I said that.
Okay.
Okay, anyway, here's the Okay. Or you could say, yes, its path is elliptical, and then you don't have to worry about it.
Yes, its path is elliptical.
But then you have to spell elliptical, which adds you
The spelling
Okay, as long as I can
Yes, it's an ellipse.
Okay, now, here's what you're going to do. Kepler's second law is the law of equal areas and equal times. So, this is kind of what you have going. So what we're going to do is we're going to look at 3 different 10-day periods of time. Now, the first one we're all going to do together so that everybody's on the same page. So what we want to do is figure out the area swept out between December 20th and December 30th. So if you look on your data, where's your data? No,
The actual sheet.
Yeah,
Usually Reese is your guy.
there you go. So on December 20th, we are at 65 degrees, okay, somewhere in here, and we've got an orbital radius of 0.309, and then on December 30th, we are at 126 degrees, somewhere in here, and we've got an orbital radius of 0.327. So what we're going to do is we're going to find this area swept out right here. So we're going to do this one together, okay? We're going to do this one together. So down below, we got to figure out how many degrees does it move through. Well, how many degrees is it on December 20th? What's that reading? How many degrees is it at?
65.
65 degrees. On December 30th, it's at
126.
126 degrees. So how many degrees did Mercury move through in this time period? 61. So I'm going to take 126 minus 65. So the angle swept out is 61 degrees. Okay? Everybody cool with that? All you have to do is subtract where it's at on the end day from where it's at the beginning. Not a big deal. So what we're going to do is use the idea that the area of the circle is pi r squared. But here's the problem. Pi r squared is if you're using the entire circle. We're not using the entire circle. We're only finding a small portion of the circle. So what we're going to do is we're going to take basically that 61 degrees and use that as a proportion constant to say, okay, we're only looking at this part of the circle. So if we were looking at like half the circle, we'd use 180 over 360, which would get us 0.5, so we'd have 0.5 pi r squared because we'd only be looking at half the circle. So the 61 over the 360 tells us which portion of the circle that we're looking at. So we're going to take 61 over 360 times pi. Now, let's talk about the radius. Radius presents a problem because the radius is continuously changing. We'll go from 0.309 up to 0.327. Okay? This is an astronomical unit. So that's, in terms of actual distances, it doesn't look like much, but you're talking like, you know, hundreds of thousands of kilometers distance, you know, because of that change in astronomical units. So there's a couple of things we can do. One very complicated and one pretty simple. One way is that we take the orbital radius on each of the 10 days, add them all together and divide by 10 and say, oh, there's our average. God-awful amount of work. We're just going to make it simple. Basically, what we're going to do is we're going to take the orbital radius on the first day, add it to the orbital radius on the last day, and then divide by 2. So we're just going to take an average of the beginning and average at the end. So somebody take 0.309 and add that to 0.327 and then divide that by 2.
0.318.
What'd you get?
0.318.
0.318. So what we're saying is that on average, Mercury has an orbital radius of 0.318 astronomical units over this 10-day period. Okay? On average, this is what it's going to be, 0.318. So what we're going to do is we're going to take 61 over 360 times pi, and then we're going to have that radius of 0.318 AUs squared. Okay? So somebody takes 61, divide by 360, multiply by pi, and then take 0.318, square that, and then I want the answer with 3 significant digits in scientific notation.
5.38 times 10 to the second, negative second.
Everybody cool with that?
Yes.
What's the one you got the radius stuff?
Here's the radius on December 20th. Look on your data table. There's the radius on December 30th. We're going to take the average of those two. So add them together to divide by 2. Boom, there you go. So, what do we get? What do we get?
5.38 times 10 to the negative second.
Times 10 to the negative second. So, now, what units do I end up in?
AUs.
Not AUs.
No.
A squared.
AU squared. Okay? So this is my area. 5.38 times 10 to the minus second AU squared. Now, what you're going to do is that you are going to pick 2 other 10-day periods. Okay? This one is up here. Pick some region down here. Pick some region over here. I don't care what, but you're going to pick your own set of 10 days. You're going to draw these vectors. Just draw them to the edge of the orbit. Don't draw them all the way out to the edge of the circle. Just draw them to the edge of the orbit. Kind of shade those in so that when I go to grade this, I know exactly which time period that you're talking about. Okay? So you can have here, here, and here. So, since everybody's numbers are different, so when you get down to number 7, area number 2, from this date to this date, okay? I don't care what the dates are. Then you can subtract the 2 areas to get theta. You're going to divide that by 360. You're going to take the average of the R. Boom, give me the area. Lay this out so that I can follow it. All you have to do is, I don't care which 10-day periods you pick, just pick 2 different 10-day periods. Be careful if you pick ones that cross over this 0 line, because then when you subtract the angles, it gets a little bit hinky. So try to avoid ones where this area is involving that 0 line. You can do it, but it's a little, you kind of have to think through what you're going to do with the angles. So, shut that down. Now, over on page 2.
I'm not on page 2.
Well, I'm just going to get you here, so just chill out. So, you're going to go to number 8. You're going to find the average of the 3 areas that you've already found. Okay? So, we're going to do a simple version of standard deviation. So, you take your 3 areas that you found. Hopefully, they're pretty close together. If they're not, something has gone horribly wrong. You're going to find the average of those 3. We're going to use that value as our theoretical value. Okay? So what we're going to basically do is find the percentage difference on each one. So here's what you're going to do. You're going to take the average, which is going to be your answer from number 8. Then you're going to subtract, like for example, that first one was, what was that first one? 5.38? Times 10 to the minus second. Then you're going to divide by the average again, take the absolute value of that, times 100. Okay? So you're going to do this 3 different times. Again, everybody's numbers are different. Everybody's average is different. The only thing I can grade is that process. Okay? So you're going to do this 3 different times. Basically, the only thing that ever changes is this number right here. Okay? Now, if you have an experimental error of 0, hey, cool. Okay? If you have an experimental error of 60%, something's wrong. So, go ahead and work through number 10. Okay. So, let's talk about number 11. So, basically, let's make sure everybody's together on number 11. So, what I want to do on number 11 is find the average between the smallest radius and the largest radius. So look through the data. What is the absolute smallest radius that you have?
307.
Yeah. 0.307? What's the absolute largest radius that you have?
0.466.
Point what?
0.466.
No, 0.467.
Yeah.
0.467?
That came off like I was like mad that you said 466, but I wasn't.
You just had to be right.
Okay. Appreciate that.
I didn't.
Had to correct it.
I wasn't trying to.
So, everybody agree. Here's the smallest, here's the largest. Right? So, somebody find the average of these 2 values.
0.387.
0.387? So, what we're going to assume for Kepler's third law is that on average, this is the distance between Mercury and the Sun. It's continuously changing, but the thing to use with Kepler's law is that you can't put in like a varying radius. You can only put in 1 radius. So this is what we're going to use for the orbital radius of Mercury, 0.387. Okay, so on average, this is how far it is. So what you're going to do on number 12, you're going to have 4 variables. Period of Mercury, period of the Earth. Radius of the Earth, radius of Mercury. So what you're going to find is the period of Mercury from Kepler's third law. So, and I tell you, let the period of the Earth be 365 days. Now, this is going to be a little bit complicated because of the fact that now we're not going to have the period of the Earth be 1 year. You actually have to deal with that as 365 days. So you can have like the period of the Earth squared over the period of Mercury squared equals the radius of the Earth cubed over the radius of Mercury cubed. Now, we can still let the radius of the Earth be
1
1 astronomical unit. So what you're going to do is you're going to go through on number 12, and you're going to substitute in everything, and then basically what I would do is I would cross multiply and then divide. And then you're going to have to either take the square root or the cube root, basically the square root because you're solving for a period of Mercury. So what we're going to figure out is what does Kepler's third law predict for the period of Mercury. Okay? Now, when you get down to question number 13, do not make this complicated. What we're going to do is you're going to figure out where Mercury is on October 1st. Okay, so look at the degrees of where Mercury is on October 1st. Then what we're going to do is we're going to figure out how many days it takes for Mercury to get back to that same point. Okay? Now, so that we don't count the same day twice, even though there's 31 days in October, and I tell you this in here, we're only going to use 30 days for October because we're going to count that day when we get back to it at the end. So, 30 days in October. We're not going to count the first day. We're going to count it when we get back around to the second, back around to that point. 30 days in November, and then you're going to figure out how many days in December it takes to get back to that point. You're going to add them up all together, get through that, stop at the bottom of page 2 before we move on. So, do that. Okay. When you get done with that, over on page 3, so here's what you got on page 3. For now, I just want you to do number 1 at the top. We're eventually going to do everything, but for now, I just want you to do number 3. So what you're going to do is this. So out of Kepler's second law, the law of equal areas and equal times, you realize that the velocity was changing. So on number 1, what you're going to do is you're going to go back to the graph. You need to do 4 distinct things. You need to find the single point where Mercury is going fastest, okay? So you're going to circle that point, go, oh, highest velocity. You're going to find the single point when Mercury is going slowest. Draw that. There's your slowest point. Then, basically, in between those 2 points, you're either speeding up or slowing down. So you're going to have a single point where it's going fastest. You're going to have a single point where it's going slowest. And then you're going to have, just draw like an arrow around the outside of it going, oh, it's speeding up from here to here. Oh, it's slowing down from here to here. If you want to shade things, if you want to shade around the outside and go, oh, the blue region is when it's going slower and the red region is when it's speeding up. It's a bit over the top, but if that's what you want to do, hey, so be it. So, here's what you're going to have. 2 distinct points, fastest, slowest. And draw these big so when I go to grade this, I'm not scrambling trying to find random little things. Oh, here's where it's fastest. Okay? And then entire regions where it's slowing down and entire regions where it's speeding up. Okay? So, do that. All right. So, even if you're not done, focus on this equation up on the board. So if you had to make a list of like monumental equations in the history of science that go, wow, this all now makes sense, this would rank right up there at the top. So now we're on to Isaac Newton. So Kepler had had his works published, everything was cool, everybody at this point was jumping on the whole idea of the Earth moving around the sun and a heliocentric solar system. And so, as the story has it, Newton was discussing Kepler's laws with a colleague, and he says, the colleague says to Newton, he goes, you know, everybody's got Kepler's laws, everybody thinks they're cool, they've been validated, but we really don't know why they work. And Newton goes, oh, here. So he goes, as the rumor has it, he goes to his desk, pulls out these bunches of paper, and go, here, this is why Kepler's laws work. And the guy says, how long have you been sitting on this? And Newton goes, I don't know, you know, but here they are. He goes, why didn't you have them published? And Newton goes, I don't know, just never really got around to it. You know, had other things to do, was inventing calculus and all this other stuff. So Newton came up with this formula. Now, there's a couple of things that Newton did and what Newton didn't do. So let me explain what this equation is. what this equation allows you to do is calculate the force between any two objects that have mass. So there's only three things that you need to know to calculate the gravitational force between two objects. The mass of each object and how far apart they are. That's it. Boom. That's all you need to know. Now, this big G, and this is on the top left corner of your equation sheet, this is what's known as the universal gravitational constant. And I'll deal with the units here in just a second. But numerically, this is 6.67 times 10 to the minus 11, and the units are newtons, meters squared over kilograms squared. Now, we're going to be using this number a lot, okay? A lot. If you know how to store numbers into your calculator, this would be a good one to store just because of the fact that we're going to be using it so often. You don't have to, but it would save you typing it in. So usually there's like an STO button on your calculator if you have a TI, okay, where you can punch it in, store, and then you assign it different variables, okay. I'm not going to give you a lesson on your calculator, but that's something you can do. It's going to make life simple. So here's what Newton proposed. He says, look, the gravitational attraction between any two objects is proportional to the mass and inversely proportional to the distance squared. Okay? So we're going to work through a simple example, and we're just so you can see how this deal works. So let's say, for the sake of argument, that we're going to look at Kendra. Okay? So Kendra's sitting here, middle of the room. Okay? And then about 5 meters away, there's a fire extinguisher. Okay? So what we're going to do is calculate the gravitational attraction between Kendra and the fire extinguisher. Okay, sounds like the name of a cool band. Oh, give it up for Kendra and the fire extinguishers. Thank you very much. So, to make the math easy, let's say that the mass of the fire extinguisher is 2 kilograms, and the mass of Kendra is 50 kilograms. Okay? So, and these two are initially separated by a distance of 5 meters, okay, which is pretty close, right? So, Kendra's here, the fire extinguisher is over there on the wall, they're separated by a distance of 5 meters. So right now, there is a gravitational attraction between Kendra and the fire extinguisher. Now, before we do this calculation, do you think it's a pretty big number or going to be a pretty small number? Small. Pretty small, and that's a good thing, okay? There's a lot of things I worry about when I lecture. One of them is not if the fire extinguisher is going to start drifting towards Kendra and get like pulled off of the wall, okay? Not going to worry about that. Could happen, probably not so much. So, we're going to do this. We're going to take 6.67 times 10 to the negative 11th, and this is why you'll see the units work out. So this is newtons, meters squared over kilograms squared. And we got the mass of the fire extinguisher, 2 kilograms. Mass of Kendra, 50 kilograms. All of that divided by 5 meters squared. So look what happens. I'm going to square the 5 meters, which is going to give me meters squared. So I got meters squared down here, which is going to cancel out the meters squared up here. Okay, those are going to drop out. Then I've got kilograms times kilogram. That gets me kilograms squared. That's going to drop that out. The only thing I have left is newtons. Now, wow. Okay, trust me on this one. This unit, more so than any other unit you will do, you have the potential to get answers that are so horribly, horribly wrong if you don't punch things in the right sequence into your calculator. So, for example, and I've had this, so one of the things you're going to calculate eventually is how long it takes the Lunar Command Module to orbit the Moon on the Apollo missions. Okay? It's one of the things you're going to calculate. I have literally gotten answers, and I've done the math. I've gotten answers longer than the universe itself has existed. Like literally, the period for one revolution is longer than the universe itself has existed. Okay? The other answers I've gotten are less than a second, like 0.1 seconds. It was like, you can't snap your fingers in 0.1 seconds and you're going to have this thing go all the way around the moon. You're going to calculate velocities of orbiting satellites. Okay? Literally, I've got answers faster than the speed of light. It's like, let's just think this through for just a second, shall we? So, trust me on this one. You have the potential to completely doink up the exponents on this deal. So, let's just, before you touch a calculator, let's just look at what's called an order of magnitude. All I want to do is look at the exponents. Okay, so look. I'm going to take 2 times 50, which is going to give me 100, right? So, which is 10 to the second. So I take 10 to the second times 10 to the negative 11th, I get 10 to the negative 9th. So up on top, I got 10 to the negative 9th, right? Now, I've got 5 squared, which is 25, which is going to be 10 to the first. So 10 to the negative 9th divided by 10 to the first gets me, all I'm saying, 25 is 2.5 times 10 to the first. Okay? So that's where the 10 to the first came from.
Okay.
Okay? So I take 10 to the negative 9th and divide it by 10 to the first. I subtract the exponents. I get 10 to the negative 10 to the negative 10th, right? Okay? So I do this just so I have some idea. I should get something around 10 to the negative 10th. Maybe 10 to the negative 9th, maybe 10 to the negative 11th. Ballpark. Okay? I do that so that when I do this calculation, if I get an answer of like 5,000, okay, something has gone horribly wrong. There is not 5,000 newtons of gravitational attractive force between Kendra and the fire extinguisher. Because if there is, that thing's going to be pulled off the wall and it's going to go flying towards Kendra. It's going to be bad. Okay? So, I just do that so that I get some idea of what I should end up with. Okay? So, somebody take and actually now run the numbers. Let me know what you get.
2.67 times 10 to the negative 10.
2.67 times 10 to the negative 10th. Anybody else?
Yep, I'm not there.
Everybody cool?
Yep.
Verified. We're good. Okay? So at this point, this is a pretty small number. Okay? When you consider the fact that if, a 1 kilogram mass to lift it is 9.8 newtons, okay? You all kind of know what that's like. Okay? This is a very, 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 very small amount of force. Now, at this point, for whatever reason, I burst into flames. Okay? I don't know what's happened, but I'm on fire. Kendra, deeply concerned for my safety, goes, "Ooh, I should go get the fire extinguisher. I'm gravitationally attracted to it. I will go to the fire extinguisher." So, Kendra gets up and starts to move, I hope rather rapidly, towards the fire extinguisher. Okay? And she cuts the distance down to 2.5 meters. Okay? We're down to 2.5 meters. So, what should happen to the gravitational attractive force between Kendra and the fire extinguisher? Should increase, right? Because the distance is smaller. So, when you reduce the distance, the gravitational force should go up. Okay? So, are we going to change anything up on the top?
No.
No, the number on the top isn't going to change. The only thing that will change is the bottom. Now, so instead of dividing by 5 squared, now I'm going to divide by 2.5 squared. And the reason I did this is this is 100. So to save you some time, it's going to be 6.67 times 10 to the negative 9 divided by 2.5 squared. So what do you get at 2.5 meters?
1.07 times 10
1 point what?
07 times 10 to the negative 9.
Times 10 to the negative 9th newtons. Now, bigger?
Bigger. No?
It's bigger.
We went from 10 to the negative 10th to 10 to the negative 9th.
But the number is bigger.
It's bigger.
So it's a bigger number, right? Gravitational force is stronger. Now, out of curiosity, somebody take 2.67 times 10 to the negative 10th and multiply that by 4. Take 2.67 times 10 to the negative 10th and multiply it by 4.
You get that number.
4 points.
Whoa, are you?
At
Wow.
1.07.
Where did the 4 come from now?
It's
Okay, look what happened. I've reduced the distance by a half, right?
It's squared. 'Cause it's
Ah, it's squared! So I'm looking at r over 2 squared, which becomes r squared over 4. The 4 flips up. This distance, or that force then, is 4 times greater. Now, let's say that, okay, at this point the fire's out. I'm good. Kendra does this. Okay. So Kendra comes back and returns to her seat. Gravitational force returns back to this. Kendra at this point is a little bit flipped out, going, I really don't like the idea of being gravitationally attracted to the fire extinguisher. So she's going to move over here to this side of the room. Okay? And instead of being 5 meters away, now she's going to be 10 meters away. Yes, so now from the original 5, we've doubled the distance to 10. So if we have the distance, it went up by a factor of 4. If we double the distance, it's going to go
4 times that.
yeah, it's going to be 1/4 as much. Okay? Now, at this point, Kendra goes, oh, this is still weird. Kendra is going to move to California. She says, I'm just going to get out of here. Okay? I can't be in the same room as the fire extinguisher.
She could just move rooms.
So Kendra moves all the way to California. Now, is Kendra still gravitationally attracted to the fire extinguisher?
Yeah.
Yes. Guess what? There is no place in the universe Kendra could go to not be gravitationally attracted to the fire extinguisher.
In the
So,
universe?
in the universe.
Deep.
Even then. So here's what would happen. Okay, and this is a pretty small number. Admittedly, this is a small number. But here's what we've got. Basically what we're saying is that, imagine this. You are in deep space. Kendra is here. The fire extinguisher is 5 meters away. And there is this attractive force. So what's going to happen is that those two would begin to drift towards each other. Okay? As long as there's no friction or anything else. So imagine the fire extinguisher is over here and Kendra's over here. That gravitational attraction, as minute as it is, would begin to cause an acceleration. Now, as they got closer, what's going to happen to the gravitational force? It's going to get bigger. So what's actually going to happen to their acceleration as they drift towards each other? It's going to increase. So the closer they get, so it becomes this reinforcing idea. The closer they get, the stronger the force, the more they accelerate. The closer they get, the force increases, the acceleration gets bigger. So they actually begin to speed up more and more and more and more and more as they get closer and closer and closer to each other. Okay? So here's what we're going to do.
How do they know that this works for like people and not just like planets and moons?
As long as you have mass, that's the only condition. It isn't like, oh, you have to be a carbon-based structure. No, as long as you have mass. So we're going to look at number 2. We're going to do this, everybody together. Go to number 2 to determine the distance from Mercury to the Sun when it's at its furthest point. What's the greatest distance, D2? Was 0.467?
Yeah.
Okay? So D2 is 0.467. The closest distance on D1 is, was that 0.307?
Yep.
Okay? So D2 on page 3 is 0.467, D1 is 0.307. So what you're going to do is you're going to calculate the relative amount of force at different points. So we're going to do this tomorrow. Okay, I just want to lay the groundwork. So we're going to finish this tomorrow. This is, you basically don't have homework tonight.
Oh my god.
Okay? So what we're going to do, and listen to me, listen to me, listen to me. What we're going to do is we're going to go to the mercury when it's at its furthest point, and we're going to give that a relative amount of force of 1. Okay, I'm not saying it's 1 Newton of force. We're just going to define that as being a relative amount of force of 1. Now, as Mercury gets closer in its orbit, what's going to happen to that gravitational force?
It's crazy. Increase.
It's going to increase. So when Mercury is at its furthest point, that's when the gravitational attraction is the smallest. When Mercury is at its closest point, that's when the gravitational force is going to be its greatest. Okay, so we'll finish that up tomorrow.